Omega prime is the new angular frequency.
Okay, so it's not derivative.
No, it's not. Yeah, I know you use that, but yeah, it's not. This is not a math class. Yeah. Omega prime is the new angular frequency with damping. Let me ask you this finally. Is omega prime less than omega? Is omega prime less than omega?
Yes.
Yeah, so it goes down due to damping. And I want you to take a look at this graph and study this graph for a second, please. Can you read what's written there? It's A naught e raised to minus b by 2mt. I mean, just this. That.
Yeah.
This is how the amplitude decreases. You can see that the amplitude decreases with time. Do you?
Yeah.
But the envelope here is exponential. You see the dotted line is an exponential graph. Makes perfect sense. Okay, to me. The third case is a forced damped harmonic oscillator. Forced and damped harmonic oscillator. So there is damping, but yet you're forcing it. The example would be that of a child playing on a swing. You push the child once, let go, the child is going to cry soon because it's going to stop swinging. Right? That's like a simple pendulum. So an intelligent dad, mom will do this. As the swing comes up and is about to go back, that's when they will apply a force. They will not apply the force at any other time, because then that would destroy the motion. Like, for example, when the swing is coming up, if they apply a force, oh, you stopped it. You know what I'm saying? Yes. So that means the frequency at which you are applying the force has to be matched to the frequency of oscillation. The oscillation has a natural frequency, doesn't it?
Yes.
Like if it's making 5 oscillations per second, not true for a swing. You know, it can't make 5 oscillations in a second, but you know what I mean. So let's say 10 oscillations in a minute, which is more possible. And then the force being applied should also be exactly 10 forces in a minute. Whatever that force is. Did you get it?
Yes.
So you could now have a damped harmonic oscillator which is continuously being forced so that its amplitude never dies down. That makes sense?
Yes.
That's what really happens in practice. So because we know we can never get rid of damping, but yet we do not want it to be damped, so what can we do? Just give it energy, an external force, but applied periodically. And how should the frequencies be? Same. What do you mean by same? What frequency should be the same? The natural angular frequency should be exactly the same as the frequency of the force being applied. So, can I represent the force as F0?
Yes.
Well, then that would be a constant force. It's not a periodic force. I need to apply. Can I apply constant force on that swing?
No.
Like, well, the child is going to. Okay. I need to apply a force that's periodic. So it needs to be F0 sine or cosine some frequency times t. I mean, I need your total concentration here. So some frequency times t, I don't know what letter your text uses, but soon I'll bring it. But what's F0? F0 is the amplitude of the force that I'm applying. Because when you apply the force, you're not applying a constant force. Look, watch how you're applying the force. It's like maximum and then you're reducing it, you see?
Yes.
Or maybe small and then you're increasing it. Either way, aren't you changing the force? So even the force applied is going to be like a sine curve. And it has a definite frequency. I'm trying. Therefore, now the equation changes. Now you need a fourth component. For a forced damped harmonic oscillator, you need a fourth component. I'll explain the diagram after you get all this. This is clear, should be clear now. I didn't want that to come in, but it just jumped. Okay. Can you explain the 4 terms to me?
Yes.
The 3 terms on the left-hand side are already clear, right? You see the damping term that's coming there, but this is the term that's the new one. That? Yeah.
Yeah, it's mass, not two mass.
When you do the differential equation, yeah. When you do the math, you only get mass. Yeah. Okay. Now, this diagram is a good one for you to understand what I'm saying. It's much better than the swing thing, which is a silly one. So, watch. What do you have here? You have a rotating disk that is rotating at a constant angular velocity omega. Do you see that? And the spring, one end of the spring is attached to that disk. And this mass is in a liquid. So what's going to happen when the disk rotates? When the disk rotates, what's going to happen? Don't you think because of the liquid, the spring is going to get extended?
Yes.
Right?
Yes.
So if you slowly speed up omega, like starting from rest, if you accelerate it, you will see that for a particular omega, the spring goes maximum up and down. You know when that will happen? If the omega of the disk is exactly equal to the omega of the spring. Doesn't every oscillating spring have a particular omega given by root k by m? Come on.
Yes. Yes. Yes.
So this spring has a natural angular frequency, doesn't it? If that disk also rotates at the same exact angular frequency, that's when the spring is excited. The spring is like, oh, that's my frequency, and go maximum amplitude. This is called resonance. I can't find a more important word in physics, which you will use in university physics too, several times. It's called resonance. What do you mean by resonance? Maximum amplitude. When does that happen? When the driving frequency, you know why I'm using the word driving frequency? The frequency you're giving is exactly equal to the natural angular frequency. That's when resonance happens. So when that happens, and we are jumping across so many steps that you will learn when you do differential equations, depending on who teaches you. This will be the amplitude. The amplitude of this oscillator is given by this big equation. Take a look at the equation. Do you know F naught? What is that? That is the amplitude of the force. You know each of these, but that's a small change here, trying to stick to what the text is using. Omega naught is the natural angular frequency now. You see? Omega naught. Omega is the driving frequency. Omega naught is the natural angular frequency, and omega is the driving frequency. Look at this equation and tell me this. If these two become equal, what happens?
Zero.
This term becomes 0. Does the entire denominator become 0?
No.
So what will you have? You'll have F naught by, remember that's a square root, so you'll have F naught by B omega. Wouldn't that be the maximum value of amplitude?
Yeah.
Because the denominator has two terms and one term is gone, so the denominator is at its lowest, which means the amplitude is? That's what I've been saying. When omega becomes equal to omega naught, you get maximum. But there is one scary thing though. What if damping was non-existent? If omega was equal to omega naught and there was no damping. If there was no damping, then what's the value of B?
Zero.
Correct?
Yes.
That is scary because anything divided by 0 in math is not defined, which is meaningless. But in physics, it becomes infinite. See, not defined can mean two things. A quantity can be not defined either because it's too small or because it's too big. Now, the math people don't care about that. They will just say not defined. Not defined because it's too small. You can't even define it. You can't even measure it. Are you listening?
Yes.
In this case, the opposite is the case. It's not defined because it's too
Big.
Ooh. So, if you set it, you drive it to oscillate at its natural frequency and there is absolutely no damping, it's going to go crazy. It'll never stop. But thankfully that doesn't happen because there's always some kind of, thank you. But the amplitude can be too big. You know, there are several cases of resonance. One that I remember is from the 1940s. There was a bridge. There is still one by the side. in Washington called the Tacoma Narrows Bridge. It was a hanging bridge, and the first time they built it, they started complaining because the cars were going over that and it would move, the bridge would move, and they said, complaining, they said, hey, what's happening? The bridge shakes. And the engineers, I don't know where they studied. Anyway, when they said, that's natural because it's a hanging bridge. It's like a pendulum, you know, a big pendulum. It's natural. Until one day, the wind was blowing exactly at the natural frequency of the bridge. And all of the times, it was set to oscillation by the driving force, which is the wind, and the frequencies were not matched. But on that fateful day, the frequency at which the wind was circulating and blowing happened to be exactly the same as the natural frequency of the bridge. And what happens now? Resonance, which means maximum amplitude. The end of the story, the bridge broke into two halves. Imagine a concrete bridge breaking into two. That really happened. Well, have you heard of, second example, have you heard of, what do you call those? Opera singers?
Yeah.
They can break wine glasses by singing.
Yeah.
That is exactly the same thing. Because they're able to produce a frequency that matches the exact natural frequency of the wine glass. And it breaks. And, you know, if you play music loud, number one, you're disturbing the neighbors. But number two, if you play music loud, oftentimes you would hear some objects in the room respond. Not always, but at certain frequencies, if you listen carefully, you will see something, you know, some loose objects, you know what I mean?
Yes.
It'll respond. You know why? Because just now the music system produced its natural frequency. Do you get that?
Yeah.
Resonance happens every day in life. And if it happens in the physics classroom every day, that's when the grades go up. Rest of the story. So in this case, I was saying omega naught is the natural angular frequency. Okay, I just had to switch from omega to omega naught just for this formula, so you know. Omega naught is the natural angular frequency, and omega is the driving frequency. And then I told you this, if omega is equal to omega naught, then A becomes F by B omega, and that is maximum, and this phenomenon is called resonance. Isn't that what I said? Then I gave you several examples for resonance. Graph, and it should make a lot of sense. On the x-axis, you have the driving frequency. On the y-axis, you have the amplitude. And you know that if you slowly increase the frequency, the amplitude is going to increase until you hit the natural angular frequency of the oscillator. See that?
Yes.
That is resonance. Isn't the amplitude maximum?
Mm-hmm.
If you go beyond that, what's going to happen? Again, the amplitude is going to decrease. But there are three graphs. One is for heavy damping, the other is for medium damping, and the third is for small damping. Does it make sense? If it's small damping, then remember, whatever the damping is, the resonance happens at the same frequency. See this?
Mm-hmm.
Which is the natural frequency of the object. But the amplitudes are not the same. If it's heavy damping, naturally the amplitude is really small. If it is small damping, it's big. That's all I wanted you to know from there. Now, these are important, Dylan. These are important. I'll throw something. These are important because radio and television tuning, you know, when you tune a station,
Yes.
you're using resonance. It's called electrical resonance, second semester. Because remember, there are so many radio stations broadcasting, and the radio waves are in this room, right? Multiple radio stations. How does your radio know which one to pick? Resonance. You're tuning, right?
Mm-hmm.
You're tuning, you're changing the value of the capacitance, actually. We can understand. But you're changing something, so the frequency inside matches the frequency at which that station broadcasts, and that's when you hear that station. Same thing with the television. When you flip the channels, that's what you're doing. It's resonance. It's always resonance. And that's why resonance is so important. So when you get to that part in semester 2, you will really understand much better. But, you know, you can buy a radio for $10. You can also buy it for $200. And it's not the size that changes the price. It is the quality of the components inside, isn't it?
Yes.
And one big quality is the resonance circuit inside, which I can't explain because you wouldn't understand now. So that resonance circuit has what is called a quality factor. All resonance circuits have quality factor. Just want you to know this, and I'll end this. The quality factor is defined. Look at that graph and look at this. This is the amplitude. Stop. This is the maximum amplitude, isn't it?
Yes.
That is half the maximum amplitude. You can see half A.
Yeah.
And there you take, this is called the bandwidth, the width of the band. So you take that frequency, the angular frequency difference between the two. Look, here isn't the amplitude half? What about here?
Yeah.
So on the lower side, on the upper side, you have half the amplitude. If you take the difference in frequencies between the two, what you get is delta omega. You see the delta omega is that difference. And if you divide delta omega by the natural angular frequency, you will get the quality factor. Just want you to write down that. Just know that the quality factor depends on delta omega by omega naught. And then I want you to, there is a reason why I wanted you to know this. How can you increase the quality factor? From that math equation, how can you increase the quality factor? Easy.
The change of omega should be bigger.
Delta omega must be
Bigger.
bigger. Delta omega must be bigger, is it?
Yeah.
So what are you looking at? Are you looking at a sharp curve or are you looking at a flat curve? If you want this part to be bigger, hello? What are you looking at? Hey, if I draw two curves, can't you make out? If I draw that, you saw the heavy damping and the light damping one. Okay, let me draw it differently so you understand. Maybe that made more sense.
Yeah.
Whereas that's half, so that would be the delta, kind of. And here if I go for half, you automatically see that the delta omega became bigger when the sharpness of resonance is reduced, isn't it?
Yes.
So that means it's a big bandwidth there. I don't want to go too much into that. For low damping, this is the formula. Approximately it's 2B by M for low damping, very low damping. That will be the end of the chapter. A magnificent chapter called Simple Harmonic Motion, where we looked at 3 types of oscillators. What were the 3 types of oscillators? The ideal one, the damped oscillator, and the forced damped oscillator. And then what we did is, for the ideal one, we worked on 2 examples. One, we worked for a long time, was the example of a spring with a mass attached, isn't it? And the other was a simple pendulum. That's all we did. That is the chapter. That is the foundation for waves. Keep that in mind, a very important chapter practically.